Imagine this for a second. There are over 60 countries larger than Norway in terms of land area. Some of them are enormous, true giants on the world map. And yet, when it comes to coastline length, only one country on Earth ranks above Norway. Not the United States, not Russia, not Australia, just Canada. At first, this feels completely wrong. If you look at a world map, Norway doesn't stand out as particularly large or dominant. It's long and narrow shore, but nothing extraordinary compared to continents. So how can its coastline be longer than countries that are many times bigger? Measuring a country's surface area is straightforward. You define its borders, apply consistent methods, and you get a clear number. That's why we can confidently rank countries by size without much debate. But coastlines, that's a completely different story. There's no single, universally accepted number for the length of a coastline. Even today, different organizations report different values. Take Canada as an example. Depending on the source, its coastline is either around 202,000 kilometers or more than 265,000 kilometers. That's not a small discrepancy. That's a difference of over 60,000 kilometers. To put that into perspective, that gap alone is longer than the Earth's circumference. And this isn't just a Canadian problem. The same inconsistencies show up when measuring the coastlines of the United States, Brazil, Chile, Indonesia, and even small island nations scattered across the oceans. So clearly something is fundamentally off. Why can't we agree on something that seems as simple as the length of a coastline? In 1967, a mathematician named Benoît Mandelbrot asked a question that seemed almost trivial. How long is the coast of Great Britain? At first glance, it sounds like something that should have a clear, definitive answer. But Mandelbrot realized something important. Different measurements were giving completely different results. And more importantly, none of them were wrong. This wasn't just a problem of bad data. It was a deeper issue, one rooted in the way we measure irregular shapes. His work would go on to revolutionize mathematics and give rise to an entirely new field, fractal geometry. But before we get there, we need to understand the core problem. Let's simplify things. Imagine you want to measure the front of a house. It's straight, flat, and regular. You take a ruler or a measuring tape, place it along the edge, and you get a clean, accurate result. Now imagine measuring something more complex, like a tree branch. It twists, bends, and splits into smaller branches. If you use a long ruler, you'll miss many of the small curves. But if you switch to a shorter ruler, you can follow the shape more closely. And if you go even smaller, you capture even more detail. Here's the key insight. The smaller your measuring tool, the longer the total measurement becomes, because now you're including details that were previously ignored. Now take that exact idea and apply it to a coastline. If you measure a country's coast using large segments, say 200 kilometers at a time, you'll smooth over all the small details. You'll skip tiny bays, narrow inlets, rocky outcrops, and small islands. The result is a simplified, shorter coastline. But now shrink your measuring unit to 50 kilometers. Suddenly, those features start to count. Your coastline becomes longer. Shrink it again to 10 kilometers. Now you're capturing even more detail. More curves, more edges, more complexity. So which measurement is correct? The answer is all of them and none of them. Each time you increase precision, the total length grows. And here's where it gets truly strange. There is no natural stopping point, no correct scale where the measurement becomes final. You can always go smaller. So why does this happen? Because coastlines and many natural forms don't behave like simple geometric shapes. They behave like fractals. Fractals are patterns that repeat themselves at different scales. If you zoom in on a small section, it looks similar to the larger whole. And if you zoom in again, the pattern continues. This property is called self-similarity. You can find fractals all over nature. The branching of trees, the structure of lungs and blood vessels, the formation of clouds, the jagged edges of mountains, even lightning bolts during a storm. Coastlines follow this same principle. No matter how much you zoom in, new details keep emerging. To really understand this, mathematicians created idealized fractals. One of the most famous is the Koch snowflake. It starts with something simple, an equilateral triangle. Then, on each side, you add a small triangular bump. Then you repeat the process again, and again, and again. Each iteration adds more detail, making the shape increasingly complex. Here's the fascinating part. The total area of the shape remains limited, but the perimeter keeps growing, without limit. In other words, you end up with a shape that has a finite area, but an infinite boundary length. It sounds impossible, but mathematically, it works. And while real coastlines aren't perfect fractals, they behave in a very similar way. This brings us to the core idea, the coastline paradox. It states that the length of a coastline depends on the scale at which you measure it. The smaller your measuring unit, the longer the coastline becomes. And because you can always go smaller, there is no single definitive length. At some point, increasing precision stops being useful, because instead of giving clarity, it creates ambiguity. You're not discovering the true value, you're just changing the scale, and that's what makes it a paradox. Now let's go back to Norway. Why does this country stand out so much? Because its coastline is extraordinarily complex. Norway is carved by deep glacial fjords that cut far inland, thousands upon thousands of islands, narrow channels and winding inlets, and highly irregular, jagged terrain. From a distance, it already looks intricate, but as you zoom in, the complexity explodes. Each fjord branches into smaller features. Each island has its own detailed shoreline. It's detail within even more detail. So when you measure Norway's coastline with increasing precision, the total length grows dramatically. That's why it ranks so high, despite its relatively small size. This phenomenon isn't limited to coastlines. It appears in many other areas of geography and science. For example, the length of rivers can vary depending on how they're measured. Borders between countries can differ based on mapping methods. Even digital maps change detail depending on zoom level. In some cases, two countries might report different lengths for the exact same border. Not because the border is different, but because the measurement method is. This shows something important. Measurement isn't always about finding a single truth. Sometimes it's about choosing a scale that's useful. So, how long is a coastline? The honest answer is, there is no single, final number. Only approximations, each one shaped by how closely you choose to look. And that's what makes the coastline paradox so powerful. It reminds us that reality isn't always clean and measurable. Sometimes the deeper we look, the more complex things become. Now I'm curious, if you had to measure your country's coastline, what scale would you choose? Would you go for simplicity or maximum precision? Let me know in the comments. And if you enjoy exploring ideas where geography meets math and paradoxes, subscribe for more videos like this.